Can you hear me? Okay, so this is just going to be a Q&A session where you guys can feel free to ask any questions and I'll try my best to answer them. So let's start things off where all good Q&A sessions start. Does anyone have any questions? Oh, and if anyone does have questions, you can go ahead and type them in the chat, or if you want to unmute, that's completely fine as well. And in the meantime, I think I'll just start going through the practice questions, if that's okay. Okay, how to find the p-value. All right. So obviously, to do that, you'd need the z table. But let's see if there's an example here that we can use. And if not, that's fine. Okay, so let's just create a hypothetical question for finding the p-value. For this one, I'm going to keep it a bit simple. So we're not going to be using specific samples. Okay, actually, no, you just, okay. So let's take an example of hypertension. So we have the average population, the blood pressure of the average population is, let's say, 110. And then let's say we took a sample, we tested a drug on it, for example. And so the drug test group, let's just toss a number out there, that's 100 millimeter, and their average was 100 millimeter mercury. Okay. So, and the standard distribution of the population is, for example, 10. And so we have our drug test group. Their average was 100 millimeters mercury. Their sample size is 12, let's say. Okay. And so what we can do is first of all, we'd have to find the standard error of the mean. And what that means is that we have our population. Our population is normally distributed. We have our population. The population is normally distributed, and we took a sample, but the distribution of groups that have 12 people is going to be different from the distribution of the total population. And so what we can do is we can correct the distribution of the population to make it so that we're looking at the distribution of samples. And I actually don't remember the exact equation, so I'm gonna have to look at. So I'm gonna have to look at the equation for standard error of the mean. So this is the equation for that. So this is the equation for the standard error of the mean, and then what we can do is we can input the numbers that we got. So we have standard deviations of the population, that's 10. So 10 divided by the square root of the sample size, or the square root of 12. I don't have the square root button on my keyboard, so we move. And then what that will give us is the standard error of the mean. And then from there, we can calculate our Z value. So just to get standard error of the mean, oh, you guys can't see this, I'm opening a calculator. 10 divided by so, well, first we need the square root of 12. Square root of 12 is 3.46, and then 10 divided by they give us roughly 2.886 or 2.89. And so that's going to be our standard error of the mean. And then to find the Z value, what we're going to do then is take the standard error of the mean, and then the difference between our group, the drug test group, and the population average divided by the standard error of the mean. So that's 110 or 100 minus 110 divided by the standard error of the mean, which is 2.89. So that's going to be 3.46. And then you can take this number. Okay, it's going to be negative 3.46 for this case. And you can just cancel out the negative, so make it 3.46. And then 3.46, if you take that to the Z table, you're going to get a number from the Z table. Use it from 3.46. And then you multiply that by 2 to get both tails. So 3.46 would give you one tail. You want both tails, so you multiply it by 2, and then that would give you the p-value. I hope that answers your question. And then we have probability equations and confidence intervals. And no worries. I'm going to start by explaining confidence intervals, if that's okay. Okay, so this is confidence intervals, the lecture, obviously. And so we have the example, which he continued from the previous lecture. And so we calculated that the limits, basically you can calculate the limits where 95% of samples that you get will fall, right? So in this area, any any data point that you take, there's a 95% chance that it falls in this area. All right. And the confidence interval is useful if we collect a lot of samples, because then you can just calculate the confidence interval for each one, and then see if it crosses into the population mean, rather than calculating the p-value for each one. And we'll look at that in further detail a bit later. If that seemed a bit confusing, I'm sorry, but we can go into a bit more detail later and we'll explain it a bit more. So in the previous example, we worked out that what is called a confidence interval for the population of anxious patients, and we estimated the confidence interval in the previous lecture, but you don't know for sure. And so you have to assume that this population has the same standard deviation as non-anxious patients. This interval will be around our sample value at 110. Okay, so basically what he's saying is that for any sample, we'd want to calculate the confidence interval for that sample. But what we're doing by doing that is we're assuming that our sample has the same standard deviation as the rest of the population, even if we're doing something to that sample that might change it. Okay. And just the same way that we did in the previous example of the previous lecture, which I should probably pull up because the whole example thing is getting annoying. Okay, great, clearly. So what I've learned is that the example has been crossing over multiple lectures, which is great, but that's fine. So basically, you've previously calculated that the standard error of the mean is 2.5, and the z value, or the z value that would give you a p-value of 5%, is 1.96. For this case, let's just apply this idea to our example. Okay. So we have our standard error of the mean is 2.8. We have all of this. We have these numbers over here, and we have a standard error of the mean of 2.8. And so what's going to happen from there is that we can, instead of calculating whether or not this value is whether or not 100 has a p-value of less than 5%, what we can do is we can calculate the confidence interval and see if that is able to hit 110. And so what we'll do to do that is we will take the standard error of the mean, so that's 3.46, and then multiply it by 1.96, which is the z value in order to, sorry, that's not, yeah. So again, our standard error of the mean is 2.98, not 3.46. And so we have 2.89, or standard error of the mean is 2.89, and then we're going to multiply that by 1.96. And what we will get is 2.89. So that gives us 5.6644. And so what we do then is we take 5.6644 and our drug test group of 100. And what we can do is 100 plus or minus. So we'll do plus, and another example we'll do minus. 5.67, just to round it off to three significant figures. So 100 plus 5.67 is equal to 105.67. 100 minus 5.67 is 94. Is 94.33. Okay? And so this range, right? So if we'll have a range of 1.5.67 to 294. So this range, this area, contains the area where 95% of the means of any of our drug test group would lie, right? So considering that if we're going to say that the drug test group, their actual mean is 100, then 95% of samples that we take out of the drug test group will have means that lie in this area, right? So it could be, for example, 103 or 90, 96 or something like that. But the idea is that the majority of samples will be between 105.67 and 94.33, and that's for the drug test group. Now, what you'll notice is that this area, right, 105 to 94, or if you want to do it smaller to larger, so 94 to 105.67. So this area does not include our population average of 110. Okay, and so what we can say is that there's a 95% chance that our drug test group does not include the population mean. All right, and so what we can do with that information is that we can say that, hey, the p-value has to be less than 5%. So we can say that it's statistically significant for this particular example. Okay. If you find anything confusing, feel free to stop me at any point, because I know like sometimes the maths can be a lot to take in, and I tend to get lost as well. So here we're looking at different sample sizes and what happens to them and what happens to the confidence interval as you change the sample size. So let's actually just apply that to the example that we've taken, right? So here we had a sample size of 12, right? So let's take a couple of samples. For example, sample 1 had 13 people, or let's say sample 1 had 10 people, sample 2 had 100 people, and then 1,000, and we'll stop there. Okay? So if we calculate the new standard error of the mean for these three samples, what we're going to find is that you end up with standard deviation, which is 10, divided by the square root of each of these sample sizes. So for 10 divided by the square root of 10, that's going to be so that's going to be 3.16. And then if we divide it by root 100, it's going to be 1. Going to be 1. Why is the n 10? Well, we're just n isn't here. So n is the sample size, right? And for these three examples, we've just decided that the sample sizes are 10, 100, and 1,000 for demonstration purposes. But for example, for the example that we did above, the sample size was 12, and so you'd use 12. But if the sample size was bigger, such as 24, then you'd set n as 24. Okay? Hope that answers the question. And so then it becomes 1 for if you put your sample as 100, and if you put your sample as 1,000, what you'll find is that it's 0.316. Okay, so you'll notice that the standard error of the mean is getting smaller. Okay, and so when we do the fancy equation up here that we did, which is just to write it down for you guys. So standard error of the mean times 1.96, which 1.96, again, to reiterate, is the value where you would get a p-value of 95% or less. And so that equals your confidence interval. And so if we do it for each of these three, so if you do it for each of these three, what you'll end up with is 3.16 times 1.96. So that equals 6.91, 6.19. And then you have 1 times 1.96, that's 1.96. And then you have 0.316, again, times 1.96. That's just going to be 0.619. Okay, sure, we'll get to it whenever we get to that point, just let me know. So what we have is we have our three confidence interval ranges, and then what we can do is we can take, again, the drug test group of 100, then 100 plus or minus. Let me just find. You know what? I'm not going to get distracted. Play simple. Let's not do that. So plus 6.19, and that's going to equal 106.9. And you do it for each of these. But the point is that you'll notice that as we increase the sample size, the standard error of the mean gets smaller. And so the confidence interval range is going to get smaller. Okay? And we can actually see that in a graph if we look here. So as you can see, the sample size is going up, and the distribution or deviation of the confidence interval around the mean gets closer, gets smaller and smaller, until it's basically almost nothing, right? If you have a really big sample size. Okay? And so what does the confidence interval tell us? Okay, is that if we don't know, is that basically if we don't know the population mean, if we do know the population mean, okay, what we can do is that we can find the confidence intervals for the population. So for this case, what we'd do is that we'd take 110, and then we'd apply all of these equations over here. So basically instead of 100 plus 6.9, it's just 110. And what that's doing is that instead of assuming that okay, I'll get to that question in just a small bit. And so what we're doing is that we're finding the 95% confidence intervals of the population, or the area where we'd expect 95% of the population to be. So what a 95% confidence interval is just where 95% of the population is, right? But we don't usually know where the population, again, this assumes, rewind a bit, this does assume that we know the population mean. So for this example, it's 110, and that we know the population standard deviation. In this example, it's 10. Usually we don't know them, and so what we'll do is, normally, is that we'll get a control group, and so we'll just assume that for the control group, the control group's standard deviation and the control group's mean is the population mean. Okay? But what happens is that because we're using the sample to estimate standard deviation, we're using the sample to estimate all of this stuff. So these results can vary, right? So we're not always going to get a perfect graph where the population mean is bang on in the middle, because we're guessing at what the population mean is. We don't actually know. And what this means is that when we measure our confidence interval for the population mean, sometimes we will get a confidence interval that does include the mean. And so we can say that it's a good confidence interval. But we don't always get that case. And that's why you end up with that's why you end up with this confidence interval over here that missed the mean, right? And basically what that's saying is that as we're taking the samples randomly, not all of them will be good samples. Okay? Now, we actually know how often our samples will miss the population mean, and that's by confidence interval. Okay? So it will miss the population mean 5% of the time, right? And that's where we get our p-value from. And that's how we can use it to tell if the p-value is less than 5%. Here it's just reiterating and like showing how you can use and do confidence interval using Movie. Okay, so what is the meaning of this interval? There's two different definitions that you can use, and basically depending on which philosophy you subscribe to, you might prefer one of them. Either you will say that samples that you collect have a 95% chance of actually containing the population mean, which I'm guessing Dr. Peter considers this to be wrong. Or you could say that 95% of samples do contain the actual true population mean, right? For this, there's really not much to say. It's just differing opinions. If you want to memorize the first one, then that's completely fine, and it's up to you. So let's take an example. We have a sample mean heart rate of 65 beats per minute, and we know that the standard deviation is 6 beats per minute. This sample had 9 patients. So we just jotted down or noted down these different data points. So we have the population mean, or the sample mean is 65%. The standard deviation of the sample is 6, and the number of people in the sample was 9. We can calculate the 95% confidence interval and 90% confidence interval using this data. All right. So we need the Z table for this, and that's where this is included. Okay. So to find the 95% confidence interval, it would mean that you would have 5% outside or 2.5% on either side for the two-tailed nonsense. Or basically, you can just spare yourself the hassle and memorize that 95% is 1.96, and just spare yourself all the details. Okay, and for 90%, it's going to be like roughly 1.64 and 1.645. Okay, just as a rough guess. But again, these aren't really like useful numbers. These aren't really numbers to memorize. You just want to look at you just want to look at where you have 0.05, and then if you multiply that by 2, or if you apply the two-tailed logic, it would then become 0.01, 0.1 or 10%. And for this one, it's 0.025, and if you apply the two-tailed logic, it then becomes 0.05 or 5%. And so the Z value for 95% is 1.96, and the Z value for 90% is 1.64. I just said that in a whole bunch of words. That's the point that you need to know. Okay, 1.96 for 95% confidence, 1.64 for 90% confidence. The explanation isn't important. All right. So the example for the 95% confidence interval, we have our standard error of the mean, which is the standard deviation divided by the sample size. Just to remind you guys, standard deviation is 6. Sample size is 9. We apply the equation, 6 divided by the square root of 9. The square root of 9 is 3. 6 divided by 3 is 2. And then so we have the Z value. And the Z value is 1.96, which we got over here, up here in this slide. And so you have 2 times 1.96 is 3.92. And then you can take the mean minus 3.92 and the mean plus 3.92 to get a confidence interval, which would look like this. This is how you put it out. Okay? And so if you want to find 90% confidence interval, again, you'd take the standard error of the mean, which is 2. And instead of multiplying it by 1.96, which is our Z value for 95%, you'd multiply it by 1.64, which is our Z value for 10%, for 90% confidence intervals. And so that would give you 1.64 times 2 is 3.8. And so 65 plus 3.28 is 68.26. 65 minus 3.28 is 61.72. And so you can draw these if you want to, or doing this completely. And you can also do this in Jamovi, but you won't have Jamovi in the exam, so I'm not really going to cover this because it's not that important. So the point of the confidence interval is that you'd expect the population parameter, or the true population mean, to lie in an area where in your 95% confidence interval 95% of the time. Okay? And so the position of the mean that you found from your sample gives you basically a rough estimate, where you'll put the area around. Okay, and that's called the point estimate, and it tells you basically how far away, or how close it would be from the other group. All right, I will go into just to explain this point a bit further because it could be a bit confusing. So here, if we use this data, these 4 numbers, there are 4 confidence intervals that we can find. Okay, the first one is the confidence interval of our drug test group, and the second one is the confidence interval of our population, right? But since you won't usually have the values for the true population, what you're going to do is you're going to just get a sample, which is your control sample, and you're going to measure their average or their mean and their standard deviation. Okay. For the sake of example, let's just say that the standard deviation for both the groups was the same. Okay. So the drug test group had an average of 100 and a standard deviation of 10. Okay. And so what you can do is sample size here is 12. And so what you can do is you can calculate the standard error of the mean for the control group, and then you can see if the drug test average is within the confidence interval, right? Now, what's being said in this slide over here is that the position of the statistic or the position of the sample mean, and so for this one, it's the control sample, the position of the control sample mean tells you the magnitude of the effect, okay? So 110 minus 100 is the magnitude of the effect. And so what this tells you is that this drug reduced the blood pressure of the drug test groups. It reduced their blood pressure by 10 millimeters mercury. All right. And then you have the precision, which you know that by the size of the confidence interval. If the confidence interval is very wide, then you can say that it's not very precise, okay? Which usually will happen with a small sample size, as we discussed in the slide over here. So if you have a small sample size, you have a wide confidence interval, and you have a low position of your confidence interval. And if you have a more narrow, or if you have a higher sample size and you have a more narrow confidence interval, then you can say that your data set is more precise. Okay, now confidence intervals you can apply this to any statistics basically. Because confidence intervals are easy to explain, right? That's why some journals like to use them. All right. Now, a confidence interval does not give you a p-value, okay? But it can tell you if the p-value is higher or lower than the confidence interval size, right? So if we have a 95% confidence interval, right, what this 95% can, then you have either two options. Either your sample is inside the 95% confidence interval, and so the p-value is higher than 5% and it's not statistically significant, or your sample is outside the 95% confidence interval, and so it has a p-value of less than 5%, and therefore it is statistically significant, but it can't tell you the actual p-value, okay? And then you have effect size, which tells you how big the effect is, right? This is what we explained over here, where we said that the effect size is basically the amount that this drug, in this example, reduced the patient's blood pressure. In this case, it was 10 millimeters mercury. That's all you need to know about the effect size, really. And so what you can do is you can do a whole bunch of fancy maths, such as Cohen's d, which is the difference in mean divided by the standard deviation, or you could do a whole bunch of other stuff. But the point is that, hey, you would want to find the effect size, is that you usually set a specific effect size even before you do your study, right? And so what this means is that let's say I want to make a drug that lowers my patient's blood pressure at least 5 millimeters of mercury, right? So that's going to be the minimum to be of clinical importance for this particular study that I'm doing, right? And so depending on what I do, then that will change the effect size, right? So for this example, the effect size was 5 millimeters mercury because I want to reduce my patient's blood pressure by 5 millimeters mercury. Now, another way to determine effect size is the value suggested by the published study or from a pilot study, right? So if there are other studies that have also used a similar drug, then you can look at those to get the effect size from those other studies. Or you can estimate it from your data after you collect it. And so what you do is for this example over here, we'd apply Cohen's d. And so you have 110 minus 100. So 10 minus 100. So that equals 10, and you divide 10 by the standard deviation, which is 10 over here. And so 10 divided by standard deviation equals 10 divided by 10, and so that equals 1. Okay? And again, standard deviation is up there, that's 10 millimeters mercury. And so for us, our effect size is 1 millimeter mercury for the example study that we're using. All right? Now, the issue of only ever using a p-value is that you can sometimes miss various very important errors, right? Or is that you can miss certain things depending on whether or not the effect size is large or small. So let's say you have a small p-value, so it's less than 5%. Okay, so let's say you have a p-value that is less than 5%, and the effect size is very large. Okay, that's not an issue because that means that your drug is working, it's reducing the blood pressure by a large amount, and it's showing statistical significance, as in it is truly lowering the blood pressure. Now, if your effect size is small and your p-value is small, then that means that you have a drug that does lower blood pressure, but it lowers it by such a small amount that we don't really care, right? And so what that means is that you have a drug that works, but it's not really doing anything that we care about. If you have a large effect size and you have a large p-value, right? So that means you have a drug that lowers the blood pressure by a lot, but you did not achieve statistical significance. And so you can't actually say that the drug works. Okay, so you don't know for sure if it's the drug working. And so here, you might have a drug that does actually work, and you just missed it by chance. All right? And if you have a large p-value and a small effect size, then that's not really an issue because you've just showed that the drug definitely does not work. All right? Okay, so just to go over the 95, just to go over this question really quickly. So you want to find the 95% confidence interval, or the 95% limit, and what you have is the mean of population, you have the variance, and you have the sample size. So n. Okay. Now, one thing to remember is that the variance is the square of the standard deviation. Okay. And so what you can do is that you can take the variance and find its square root to get your standard deviation. And then you want to find the standard error of the mean, which is standard deviation divided by the square root of the sample size. So if I want to toss, could we solve this equation? Okay, in just a bit. Sure. So let's say we have the mean of a population as 50. We have a variance of 100, and that's standard deviation squared again. And our sample size is 16. Okay? So what we want to do first is find the standard error of the mean. So that's standard deviation, so 100 divided by the square root of the sample size. So that's equal to 100 divided by 4 equals 25. Okay? So we found the standard error of the mean. next we want to find our actual range. Okay, so what we do is we want to find 95% limits. And so what we want to do is we want to go to the Z table first and find the Z value that would give us 95% limits. And again, as we've said, it's 1.16. And so what that gives us is gives us 49. I'm just going to rewind because I kind of did a whoops. So we have variance equals 100 from the very beginning. So 100, we find the square root of 100 first. Okay. So what that means is our SD is equal to 10. We want to find the standard error of the mean, so that's 10 divided by the square root of 16, which is 4. Okay, using this equation. So 10 divided by 4 is equal to 2.5. And then 2.5 multiplied by 1.96, which, as we said, is the Z value to find 95% confidence intervals. And so that would give you 4.9. And so this would be the number that you'd use for your confidence interval for this case. So 50 plus 4.9 and 50 minus 4.9. And so we have 54.9 on one side, and we have 45.1. Okay, so our final confidence interval is going to equal 45.1, and so 54.9. And so this would be our final confidence intervals. I hope that answers your question. If it doesn't, go ahead, rest me in the chat or let me know. Okay, this question after this question, p-value, we have mean difference is 7.3. Is it okay if I just get back to this one once we're done with the confidence intervals lecture? I'll get back to you with the p-values. All right? So we have p-values and confidence intervals. So we make a basis of whether or not to reject the null hypothesis. So we make the basis of whether to reject the null hypothesis using the p-value. All right. But we can make mistakes by using the p-value, which we mentioned here. So the p-value is small, but the effect size is small. And so the drug is useless, but we're saying that it's helpful, or the opposite could happen. And so we can use confidence intervals to look at whether or not that's the case, right? And we can also help decide whether or not the magnitude of the effect or the effect size is actually worth looking into. All right. So here we have a bunch of confidence intervals, right? And we've drawn two lines. Now, importance is the line of our effect size, okay? And then we have the null value, which is the true population mean. If the confidence interval crosses the null value or crosses the true population mean, then it's not statistically significant. Okay, so we have a bunch of examples here, and we're just going to go through them one by one. So in example A, we have this confidence interval. Now, you can go ahead and type in the chat if you guys want to. Is this statistically significant? Okay, it is statistically significant. Now, is the effect magnitude large enough to be considered interesting? All right, so for this example, we have it's both statistically significant and it's interesting. All right, so for B, we have a confidence interval that isn't crossing the null value, but it is crossing the value of importance. Okay, so what we look at here is that it is statistically significant because it's not crossing the null value, but it might not be interesting because it's crossing the important because it's crossing the important line, or the effect magnitude line, but there's also part of it outside. Now for C, it is statistically significant because the null value, because it isn't crossing the null value, but it's definitely not important because it's not even slightly crossing the important line. Okay. For D, it is crossing the null value. So what that tells us is that it's not statistically significant. However, it's also crossing the line where we set our effect size. And so what we can say is that there is a chance that this treatment D, is of clinical importance, or we might want to look into treatment D a little bit more just to make sure. Now for treatment E, it's crossing the null value and it's closer to the null value than the line for clinical importance. So we can definitely say that treatment E is completely worthless, don't use it. All right, so here we're just answering the questions. And again, this is another example. So you have A, which is not significant, and it's not important. So you have A, which is statistically significant, but it's not clinically important. And then we have a B, treatment B, which is statistically significant and it's clinically important. So because it's above the line of effect magnitude. We have treatment C, which is crossing the null value line, so it's not statistically significant. And finally, we have treatment D, which is both crossing the null value. Okay, so we can say it's not statistically significant, but it is also crossing the line of clinical importance. So there is a chance treatment D might be clinically important, but we don't know that yet, right? And so this is just the different samples. And as you can see, larger sample size gives you a more narrow confidence interval. All right. So in treatments A and B, which are these two, both confidence intervals lie above 100, which means they're both statistically significant. Okay. The midpoint is also above 100, right? Okay, so the midpoint of each is 6 standard errors above 100. So the Z values and the P values are identical. All right, but because of the difference in the confidence interval, how did we know that they have the same value? That is an excellent question. I have no clue. Okay, I'm just assuming that it's right based on what's written here. Okay, and I'm basically guessing that there's information that's hidden from the rest of humanity in this example. Okay? All we're saying is that these have identical p-values because both of them are 6 standard errors above 100, right? Either the numbers are hidden or there's some complicated maths that's way too out of scope right now. Okay, but point is p-values are the same. But when you look at the confidence intervals, they're giving you very, very different information, right? And so in A, the mean is close to the 100 null value. And so it's not really, and so the treatment for A isn't really helpful, like doesn't really say that it's helpful, but the treatment for B does say it's helpful. Okay, so in A, the mean is close to 100, which tells you that the effect size is less important than the effect size that you get in B. All right? And so in outcome C and D, both confidence intervals cross the null value, which tells you that it's not statistically significant. And the p-value is the same, again, for unknown reasons. But again, you get two very different stories when you look at the confidence intervals. In treatment C, the confidence interval does not cross the important line, so we know for absolute certain that there's no chance that treatment C is going to turn out to be helpful, or there's a very low chance that it turns out to be helpful. But in treatment D, it's more likely that the effect size is larger. And so if you do the test again for D with a larger sample size, you might get a different result. All right? Okay, so the confidence interval can be used to estimate power. Okay, and so if the confidence interval is crossing both the null value and is crossing the importance line, then you can say that this study has low power. What is power? Okay, to give you the summary, power is the ability to detect a true difference in effect. Okay, so if you have a drug and it works, your power is how good is your study at telling you that this drug works. All right, and bear in mind this is different from the p-value. Okay, you have your p-value and you have your power, and they're very separate. Okay, so if your 95% confidence interval has an interesting effect size area, so that's over here, and it also includes the null value, and also a bunch of uninteresting small values that nobody really cares about, then you might want to collect more data, right? Because you might want to look at whether or not there's a chance that that your drug does actually work, or your treatment does actually work. And so that might be able to push it towards being statistically significant and being of clinical importance. And so the width of the confidence interval can help tell you whether or not you have enough data, right? So in this example, the minimum desired blood pressure change that they're looking for is 3 millimeters mercury, right? Now, as you can see in examples A and B, it's crossing both the null value, right, which is okay, so it's crossing both the null value of 0 and the limit for importance, right? And so both of these, what this is telling you is that in both of these examples, you're not really you don't really have a large enough sample size. Now, in example C, it's over the importance line, like completely over the importance line, and it's not touching the null value. And so what we can say is that the treatment in C definitely works, and you have a large enough sample size that you can observe that difference. Okay, and so this is a quiz. If you want to go over it, which of the following statements about 95% confidence interval is correct? So it has a 95% chance of containing the parameter. It has 95% of chance of containing the statistic. 95% of such intervals will contain the parameter. 95% of such intervals will contain the statistic. Okay, so just to recap, for any sample that you take, and you find it's 95% confidence intervals, 95% of samples that you take, okay, will have the parameter inside their confidence interval. Okay, and so that immediately eliminates choice B and choice D. Okay, because we know that it's the parameter we're looking for, not the statistic. Now, why is it choice C and not choice A? And it basically goes back to, if I can find this slide up here, about being very specific with your definitions and overly fancy. And long story short, in this course, we're going to prefer the frequentist definition, which is 95% of intervals will contain the parameter, instead of looking at probabilistic definitions. Okay? Now, if the 95% confidence interval does contain the null value, what can we do? Okay? Now, if the 95% confidence interval does contain the null value, then we can say for certain, right, that it's not statistically significant, that the p-value is above 5%, okay? And so we're not going to reject the null hypothesis, we're going to accept the null hypothesis. Okay, now I know we made this whole long story about effect size and about how we have to collect more data and all of this fancy stuff. But long story short, if you have a 95% confidence interval and it contains the null value, accept the null hypothesis. All right? And reject the alternative hypothesis. So, what should we do if the 95% confidence interval contains the null value, but also the important value? Okay? Now, if it contains the null value, then, as we said in the previous example, we accept the null hypothesis and we reject the alternative hypothesis. All right? So that eliminates options C and D because they're telling you to reject the null hypothesis, and as we said, you shouldn't do that. Now, why is it option B and not A? Well, it comes down to the fact that it holds a value that's practically important. Okay? Since it holds the null value and a practically important value, then what you want to do is you want to collect more data to basically check your answer. Right? So you want to collect more samples to check, is this result correct? Right? And so that's why option B is correct and not option A. So what should we do if the 95% confidence interval doesn't contain the null value and its lower limit is better than the value of practical importance? Right? So what that means is that the 95% confidence interval doesn't contain the null value, right? So reject the null hypothesis. And the lower limit of the confidence interval is better than practical importance. So what that means is that the confidence interval doesn't touch the value of practical importance. All right? And so what that means is that your study was successful. You both proved statistical significance and you proved that there is a significant effect size, that it has practical importance. And that's why the answer here is A. All right, so just going back to the p-value example. So find the p-value. The mean difference is 7.3. Let me just do this down. Okay, so mean difference is 7.3, n is 25, SD is 19. Okay? So, we have these data points. What do we do? Well, first off, we want to normalize our standard deviation, right? We want to make it into the standard error of the mean, okay? Because again, for samples, standard deviations aren't as helpful as standard error of the mean. So first thing to do is to divide the standard deviation, which is 19, divided by the square root of the sample size, right? I cannot be bothered to get the square root symbol again, so we're just going to type it manually. So that's equal to 19 divided by 5. 5 is the square root of 25. And then we end up with is equal to 3.8. All right. So we have the mean difference is 7.3. We have the standard error of the mean, 3.8. So 7.3 divided by 3.8 is equal to 1.92. So what we can do is we can go to the Z table, right, and we can find what does 1.92 mean, right? So luckily, we do indeed be having a Z table in this PowerPoint. So we have 1.92 is our Z value. And so we'll go to 1.9 on the side. And then to get to 1.92, you want to look at the other axis. So here's 0.02, here's 1.9. We look across. I don't know if you can see this. Okay, so we want to look at the Z value of 1.92, and you end up with a probability of 0.0274. Okay, so let's note that down. Okay, so once we have this probability, okay, we want to multiply it by 2. Why are we multiplying it by 2? Well, if I use awful handwriting to draw a graph, what that's going to look like, other than looking horrible, what that's going to look like is this. So we found our Z value of 0.0274. We found our Z value of 1.92. We found the probability 0.0274, and that's this shaded area over here. Okay. Now we want to find both tails. Okay, because the p-value is the probability that it's basically this, like the probability that it's okay. I can't find the words right now, but basically this area over here, the p-value is the probability that it's outside of this area in the middle. So if I color, okay, so if this area, if I like shade it in really, really not well, the p-value represents not this red region. Okay, so further away from the population mean than all of this red area. And so to do that, we take the probability and we just multiply it by 2. So 0.0274 multiplied by 2, and what you're going to get is 0.0548. Now, because this p-value is above 0.05, what that means is it's above 5%. And so we can accept the null hypothesis and reject the alternative hypothesis. I hope that's clear. No problem. So I believe that's another lecture that you guys wanted to explain. So I'm not sure what you want me to explain by probability equations. Hiba, if you could please clarify, like, is it the probability distributions lecture, or is it something else? I will just be sat here if anyone has any questions. Ah, okay, gotcha. Okay, since I was asked to explain this lecture as well, let's just go through it really quickly. So we have statistical inference. That's the procedure for generalizing based on a small amount of information. But basically what we're doing is we're saying we took a sample, we found data based on that sample, and the rest of the population, they're sort of similar to the sample, so we can say that they're the same thing. Okay? So there are two types of inference that we can have. So there are two types of inference that can be drawn about a target population. We can estimate a parameter or we can test a hypothesis. Inferential statistics is how likely it is that the sample is the exact same as the population. All right. So what does probability mean? We have a clinical trial saying that 30 patients receiving a treatment for X do better than 30 similar patients getting Y. So what we're saying is that the hypothesis is that X is better than Y, right? How do we know for sure, okay, that X is better than Y? If the uncertainty is low, the study conclusion will be well-founded. If the uncertainty is high, then we have to basically do more studying, right? So it's crucial to measure uncertainty using an appropriate tool. We call that tool the theory of probability. Probability is basically just us studying randomness. So why do we study probability? There are two things that we do in statistics. We do descriptive statistics, which is where we take data, organize, visualize, and summarize it. And then we do inferential statistics, which is where we take that same data and then we look at the general population, say that our sample is similar to the general population. And so the values that we got from our sample mean, our sample standard deviation, is similar to the population mean and the population standard deviation. This slide is basically just showing you the process. We take a sample using sampling, so random, and then we make inferences based on what we find in that sample. And again, samples can be good samples or they can be bad samples. All right? So probability is a measure of chance, right? So how likely is something to happen? So if you toss a coin, what is the chance that you get heads? All right? Now, when you measure probability, the smallest number that you can get is 0, and the largest number that you can get is 1, right? So basically 1 represents something that is impossible to happen, something that can never happen, and 1 is something that definitely will happen. Okay? Most events usually have a probability that's between 0 and 1. All right? So unlike length, okay, which is expressed in units, so length is, we usually measure length in numbers. We usually measure length in meters. Probability doesn't have units for it. All right? Now, there's a belief that people have that's kind of a mistake, that if you don't know the patients in your sample, then it's random. But actually, taking a random sample is a very annoying and very rigorous process, and it's very systematic when you do it. Okay? And so when you're performing statistics, you can get random variation, which is because not all of your samples are the same. So a random variable is a variable that comes out by chance. And they can be discrete or continuous. This is spoken about in another lecture, but basically discrete will have set values. So a 1, 2, 3, 4, such the numbers on the dice, right? You don't get 2.5 on a dice unless you're very skilled. Or they can be continuous, so height in meters, it can have decimals. Okay? And a random sample is a sample where every single member of the population has an equal chance of being selected. Okay? And the selection of each member of the sample is made independently. Okay, so you can't just go up, knock on a house, and then say, all of the family, I want them in my sample, right? Because that wouldn't be very random. Okay, first of all, okay, and that's because the selections weren't made independently. You just selected one, and then you selected all of the others based on that first selection. All right? So, the way to define probability, okay, experimentally that is, not in theory, is that when we do an experiment n number of times, and a specific event happens m times, then the ratio of m events over n experiments will approach a fixed limit, or the probability A. So what does that mean in English? Well, basically what we're saying is that let's take flipping a coin. Now, if we flip a coin 10 times, right, and we say event A is heads, now heads will occur a random number of times. It might be 5, it might be 4, it might be 6. Okay? But as we keep flipping the coin over and over and over again, let's say we flipped it 100 times, let's say we flipped it 1,000 times, the number of times that we get heads will gradually become closer and closer to 50%. All right? And so the probability of event A is the number of times that A happens, or in our example, the number of times that we get heads in the number of times that we do the experiment. And so in our case, the number of times that we get heads when we flip an infinite number of coins. All right? So an experiment is a clearly defined procedure that leads to an outcome, such as flipping a coin, and an event is a bunch of outcomes. So for flipping a coin, it's heads, or it could be heads, or it could be tails. And the sample space is a list of all of those events. So for flipping a coin, it's heads, tails, and that tiny, tiny, tiny probability that it exactly lands on its side. All right, so a fair coin will have equally likely chance of getting heads or tails. And so tossing a coin is an experiment, and our events are heads and tails. And because these two occurrences are single events, then we can call them elementary. Right? And for a fair coin, they're both equal, and they are both 50%, or 0.5 in numerical terms. So let's take an example where we're throwing dice. Find the sample space for the experiment, or find all of the possible events. And let's just give a bunch of examples for events that are in the sample space. Okay, so throwing a 6-sided die will lead to a sample space of the 6 sides of the die, or the numbers 1 to 6. So when you roll a die, you can get 1, you can get 2, 3, 4, 5, or 6. And a couple of examples of events is getting an odd number. So that's one possible event, which would leave you with 3 simple events. And so the simple events are each of these individual ones. So 1 is a simple event, 2 is a simple event, 3 is a simple event, 4, 5. Each of them are simple events. But getting an odd number isn't a simple event, because when you set getting an odd number as your event, there are 3 different events that can give you an odd number. Okay? Whereas if you have your event being getting the number 2, then there's only one possible way to get the number 2, which is to get the number 2. What do you mean by simple event? A simple event is to give you the basic idea, when you roll a dice, any unique outcome is a simple event, right? So anytime you get specifically 2, that's a simple event, and stuff like that, right? The point is that unique outcomes are each their own simple events. All right. If you have an event that contains more than one unique outcome, then it's not simple. Okay. Hope that clears that up. Okay. So what is the list of 2 possible outcomes? rolling 2 dice, you're going to get the events for the red die, the events for the blue die. All right, so this is just a quiz. What's the complete list of all possible outcomes of the following experiment? A single roll of 2 die, one of which is standard, and the other one has 3 on all sides. And so the sample space would just look like, for this quiz, the sample space would just look like 1, 2, 3, 4, 5, 6 for this die, and then 3 for the other die because it has 3 on every side. All right. Okay, so let's take a couple of operations for the events. First off, we have an intersection, which is saying both A and B. So if we toss a coin and roll the dice, what we're saying is this event will have heads, and also we will get 3. All right. Now in an OR, what we're saying is that I want to get either A, so either heads, or the number 3, or both. Right? And then we have the complement, which basically means not. Okay, so the complement of A is not A. So if you have A and the intersect thing with the complement of A, what that basically means is A and also not A, which can't happen. So if there is an event that doesn't have any, if we have an event that doesn't have any simple events inside it, we call that the null event. Okay, and so the probability of A and also not A is 0, right? Because you can't have both heads and not heads at the same time. Okay, and so the probability of getting the complement is the same as the probability of getting the complement, or the probability of not A, is 1 minus the probability of getting A. Or in other words, the probability of getting heads of not getting heads when you toss a coin is the same as 1 minus the probability of getting heads. All right. So Venn diagrams can be pretty helpful if you want to show operations. Here we have 2 separate Venn diagrams. The one on the left here shows you an intersection or an AND operation, which is this first one. And then the one on the right shows you the union, or which is the OR operator. So A or B. Okay. Now there's a bunch of examples over here, which looks at probabilities. This one, it's looking at sample space and what is the chance that you get heads both times. So the sample space is 2 tails, tails then heads, heads then tails, and 2 heads. And so what's the chance that you get 2 heads? Well, there are 4 possible outcomes, and 2 heads happens in one of the outcomes. So it's 1 out of 4. So here's another example. I'm just going to skip through it because the answer is here. Now, this is another example, which is that in 100,000 individuals, okay, the event, and so in this event we have surviving the first year of life, happens 99,149 times. Now, is this an experiment? Okay. Well, the answer is yes. Yes, it is. Why is it an experiment? Because we've defined a bunch of rules and it has possible outcomes. Okay? And we've come up with a process that will give you those outcomes. So what's the probability that an infant will live to see their first birthday? Well, we have, so what we can do for that is that of the 100,000 individuals, 99,000 and whatever live to see their first birthday. And so it's 99,149 divided by 100,000, which would give you 99%. All right? So relative frequency is the frequency of an event, is the number of, divided by the total. Basically, it's the percentage of times that any event happens. All right, so if I just skip to the end, the relative frequency has two things. The total relative frequency of all outcomes is 100%. Okay, and none of the outcomes can have a relative frequency of less than 0. All right, those are the two things. So to find the relative frequency, what you do is you take the number of times that the event happened divided by the total number of experiments. Okay, and that gives you the relative frequency. So for frequency, we have the number of students taking 0 maths courses is 7. The total number of students is 35. So 7 divided by 35, okay, multiplied by 100, that's 20%. All right, and then they repeated that process. 14 divided by 35, multiplied by 100%, that's 40%. 10 divided by 35, and I think you get the idea. Okay, and then you can use that to find the probability. You just divide by 100. So 20 divided by 100 is 0.2, 40 divided by 100 is 0.4, 29 divided by 100 is 0.29, and so on. And so you can map out the frequency on a bar graph. So the properties of probability, again, it has to be more than or equal to 0 and or less than or equal to 1. Okay, so basically it's between 0 and 1, and the probability of the sample space is always 1. So the probability of S, which is the sample space, is always 1, because when you do an experiment, something has to happen, and the sample space is all possible outcomes. Okay, so here's an example. You're rolling a 6-sided die. Now let's take event A, and we've decided that event A is rolling a 5 or a 6. So what is the probability of A, and what is the probability of not A? So when we roll the 6-sided die, the probability of A is the chance that we get a 5 or a 6. Okay, and so that's 2 out of 6, because there are 6 outcomes when you roll the die. 5 and 6 are 2 of them, so it's 2 out of 6. And not A is 1 minus 2 out of 6, so it's 4 out of 6. Okay. Now, if you have 2 mutually exclusive events, and these events are A and B, then A intersection B, or the chance that A and B happen, is the null event, and the probability of both of them happening has to be 0. Now, this is different from the complement. Why is it different? Because event A and event B are 2 separate events. All right, so let's take, for example, the event A is getting a 6 when you roll the dice, and event B is getting a 3 when you roll the dice. Now, you can't get both a 6 and a 3 in one dice roll, and so that's why it produces the null event. All right, And so two events that can't co-occur gives you a probability of 0. Yeah, so this is just an example. Right, so event A is a baby is born that weighs less than 2,000 grams, and B is that they are born between 2,000 and 2,500 grams. Then you can't have a baby that's both less than 2,000 grams and between 2,000 and 2,500 grams. All right. Now again, this is different from complement because what complement's saying is that event A is 2,000 grams, and the complement of A is just not less than 2,000 grams. All right? Okay, so this is just an example. I'm not going to go through it. So there's an additive rule, which is the union, or the probability of A or B, is equal to the probability of A plus the probability of B minus their intersection, right? Now, why is that? So let's just enable editing, please. Okay, so we have the additive rule of probability. And so what this means is that if we draw a nice Venn diagram, okay, so if we draw a not very nice Venn diagram, what we're going to have is that the probability of the union, which if I just use a highlighter, so in yellow is the union. So the union is everything basically in this sample, is A or B. So the probability of the union is equal to the probability of A plus the probability of B minus the intersection. So why are we subtracting the intersection? It's because if we only do the probability of A plus the probability of B, then we're counting the intersection twice. All right? Now, the exception for this is if they're mutually exclusive, right? Because if they're mutually exclusive, there's no intersection. So we end up with the union is just the probability of A plus the probability of B. Again, this is for mutually exclusive events. All right? Here's just an example of the calculation. Feel free to go through it yourself. Okay, so for independent events, this is just a bit of a typo, so I guess it's a bit of a typo. So if event B is not affected by event A, then they're definitely independent, okay? Which basically means that if the probability, so basically what that means is that the probability of event B, if A has already happened, then equals the, okay, so So if the probability of event B, given that the probability of event A has already happened, then is equal to the probability of B, then A and B are independent, right? So let's take a quick example just to illustrate this. All right. So we're going to take so this one's going to be dependent, and then the next one's going to be independent. All right. So let's say the probability of event A in example 1. So let's say the probability of event A in example 1. Sorry, let's say event A in example 1 is it rains, okay? And event B is you will wear a rain jacket. Now, if it rains, then you're more likely to wear a rain jacket than if it doesn't rain, okay? And so what that means is that the probability of you wearing a rain jacket, which is event B, given that it's raining, is not equal to the probability of event B normally. Okay? And so that's example. And so these two events are not independent because they're affecting each other. Now, in example 2 over here, we have, let's say event A is it rains, and event B is I will have pizza for dinner. Now, whether or not it rains, okay, basically the weather does not make me have pizza, but it also doesn't stop me from having pizza. All right, so what that means is that me having pizza isn't affected by whether or not it rains. And so the probability of event B, which is me having pizza, given that it's raining, is still the same as the probability of event B normally. Okay? And so with that, we're going to be taking a new rule. So the multiplication rule basically tells you that if you're finding the intersection, okay, what you want to do is you want to find, and so you want to find the probability of A intersection B, or A and B. So the probability of it raining and me having pizza. Okay, so what the equation for that is the probability of A multiplied by the probability of B given that A happens. All right, and it can also be the probability of B multiplied by the probability of A given that B happens. All right, now if A and B are independent, then what the equation ends up being is the probability of A and B is equal to the probability of A multiplied by the probability of B. All right? So what we do is, what we're going to be taking in this example is that we have two adults, 18 and 40, okay, between the age of 18 and 40, and the probability of adults in this age region not having health insurance is 0.123. Okay? And so, what's the probability that two individuals that we select don't have insurance for question 1? And then question 2, is what's the probability that they both do have insurance? And so the way you solve question 1 is since the probability of A, which is our first person, is 0.123, and the probability of B, which is the second person, it's also 0.123. And then what we can do is we can say that they're both the same thing, so that's what's happening on this line. So the probability of A is equal to 0.123. The probability of B is also 0.123. And so applying the multiplication rule to find their intersection, right, we have the probability of A, which is 0.123, multiplied by the probability of B, given that A has happened. Okay? Now, for this particular example, these two people are completely unrelated, right? So whether or not the first person we choose, right, the 22-year-old man, has insurance or not, will not affect whether or not this 37-year-old man also has insurance. Okay? And so what we do there is that the probability of A multiplied by the probability of B given A just becomes probability of A multiplied by the probability of B. And so we replace this with numbers, and so we end up with 0.123 multiplied by 0.123, and that equals 0.015. Okay? And then the second part is that they both have insurance. And so we want to find both of them not having insurance. Okay, and so first off, we have to calculate both of them having insurance. So the first thing we have to calculate is the probability that each one of these two men has insurance. Okay? And luckily, because their probability is the same for both, then what we can do is the probability of not A, okay, or 1 minus the probability of A, is equal to a 1 minus 0.123 or 0.877. Now, this is the exact same for person B since their probability is the same. And so we have the probability of them both being insured, okay, or the probability of A complement, and again A is the man not having insurance, multiplied by the probability of B complement, and B complement is the event where person B does have insurance. Okay, and so you just multiply these two numbers together. So 0.877, which is the probability of A, and 0.7777 for person B would give you 0.769. All right. Now, independence is not the same as mutually exclusive. Right? If you have two events, A and B, independence is where A does not affect B. Okay? Whereas mutually exclusive is where A and B can't happen together. All right? I think that's it. I think the rest is just examples. Okay. So that wraps up that lecture. Does anyone have any questions for it? All right. Thank you very much. Okay, I guess I'll just wait here until someone asks a question. All right. What are the odds against getting exactly 2 heads? Oh, when a coin is tossed 3 times. Okay, so to find that probability, okay, so first off, the answer kind of can't be 5 over 3. But let's go through it together. All right, so I'm just going to open a new slide. Go to the annoying text boxes. All right, so we have 3 coin tosses, 3 coins. And we want 2 heads. Okay? So, for any of these events, we have. So for any of these events, we have 50% for each one. So either you're getting heads or tails. Okay? And it's a 50-50% chance for each. Okay, so we have heads. You know what? I don't know why it is. Okay. 3 coins. Heads 2 times. Then we have heads equals 0.5. All right. So if you toss a coin 3 times, there are 8 possible outcomes. And that's 2 times 2 times 2. Okay? And so the probability that we get heads twice is, what we're looking at is that you want 2 heads and 1 tail. Okay? And again, these are mutually exclusive events. And so there are 3 possible outcomes that can give us 2 heads and 1 tail, right? Either it's heads, and then tails. Heads, tails, heads, or tails, heads, heads. Okay? Those are the 3 possible outcomes where we get exactly 2. Now, because there are 8 outcomes, so the probability of getting exactly 2 heads when you toss a coin 3 times, that's going to be 3 out of 8. Okay? And so the odds against getting exactly 2 heads is going to be 5 over 8. Now, I think what you're referring to is going to be the ratio for and against. And so to find the ratio of the two, what you'd do is you'd find the number of events where your event does happen. So let's say that heads twice is event A. So we want to find the number of times where A happens, and we're going to put that as the ratio to the number of times that A doesn't happen. So the ratio of 4 heads happening is 3 to 5, okay, which is it happens 3 times and doesn't happen 5 times. Or the ratio against it is 5 to 3. Now, please bear in mind that ratio is completely separate from probability, because with probability, you're looking at how many times does event A happen out of all 8 events, whereas with ratio, you're looking at how many times does event A happen against not getting event A. Okay? Hope that was clear. All right. Does anyone else have any questions? All right, so in the meantime, I'm going to go over the practice questions that you guys were given. Okay. So the first question, which of the following statement is the most accurate definition of biostatistics? So we have biostatistics focuses on the cause and distribution of diseases and medical conditions. Well, no, it doesn't. The biostatistics studies disease and the risk factors associated with specific population to prevent and control disease. Again, biostatistics is all about collecting data and analyzing data. And so for option C, biostatistics emphasizes collecting, analyzing, interpreting medical data. That's the correct option. And biostatistics is another name for epidemiology. Well, that one's wrong. And so defining biostatistics, it's the act of collecting, analyzing, interpreting data, and then making inferences on the population based on that data using statistical methods. And because it's biostatistics, so it applies to biology. Now, epidemiology is where we study diseases, what causes diseases, and what can prevent those diseases. All right. Now, we have descriptive statistics as our second title. Which of the following statement defines a statistic? A numerical characteristic of a population. Well, that one's a parameter because it's of a population. An observation which is extraordinarily large or small compared to other observations in this data set. That one's an outlier because it's very far from the other observations in the data set. A numerical characteristic of a sample. That is a statistic, and so a numeric characteristic, that could be the mean, the standard deviation, and so on. And D is the degree of precision required in a data set. I'm honestly not sure what that is. Then again, I am starting to get a bit fried, so forgive me if I'm a little slow here and there. But the point is that the answer for this one is C. So, next question. The time being registered into a study until a person develops the disease that we're studying is classified as which of the following? Is it nominal data, ordinal, outliers, or time to event? Now here we have two data points that we're studying. Okay, first of all, do they develop the disease of interest? Yes or no? Okay, and then the next point is how long does it take for them to develop that disease of interest? And as such, it's a time to event data. Okay, and basically time to event data is any time we're studying how long does it take for something to happen. Right now, this could be develops the disease of interest, this could be curing the disease of interest, or it could be death. Just kind of dark and morbid. All right, so next question. So frequency distributions. We have the following sample data for the number of maths courses taken by second-year medical students as a baseline. They're asking us to complete the table. All right, so this one's going to get a bit dicey. One second, share. All right, so first of all, we have, so this is the information that we're given. So let's start by finding the relative frequency of the number of people taking 2 maths courses. And so that's going to be 19 divided by 100, right? Because the relative frequency is basically the percentage, the number of people, the frequency over the total group represented as a decimal. Okay, it's all basically the percentage of people in that specific group from the total sample. So for this one, it's just 19 divided by 100, so that's 0.19. Okay, and then we have this row complete. So for 0.35, what we do is we have to work backwards. So for this one, it's whatever this number is divided by 100 is equal to 0.35. So working backwards, 0.35 times 100 is going to give you 35. All right. And then to find the rest of the numbers, what we need to do is we need to work with the cumulative frequency. Okay. So what the cumulative frequency is basically it starts at 0. And the idea is that by the end, we're going to add up the people until they reach 100. All right. So first of all, okay, so in total it has to reach 100. And then so first of all, we have 27 people as our cumulative frequency, right? And we have 19 people in this group. So the previous group would have had to have 27 minus 19, right? Which is 8. So our previous group had a cumulative frequency of 8 and also a frequency of 8 because there's no other group before them. And so their relative frequency is 0.08, which we found by 8 divided by 100. All right? So for our cumulative frequency for the next group, that's going to be 27 plus 35. So that's 27 plus 35, that's 62. And for the next group, we take the 62 and we add 15, sorry. We add 62, add 15, and that's 77. And so then we have this portion of the table filled. It's looking very nice. So next we want to find the row of people that took 5 maths courses. And so to do that, what we do is 91 minus 77. So that's going to be 13, 14. And so the frequency of people in this group is 14. And then the relative frequency is 14 divided by 100, or 0.14. Okay? And now for the last group, the cumulative frequency has to be 100. All right? And as a result, the frequency is 100 minus 91, which is 9. And the relative frequency is 0.09. All right? So the next question. So we have calculate the mean, median, range, and standard deviation for the following set of weights. Which of the following is correct? Okay. And so what you want to do is a whole bunch of maths. But basically, let's start with the mean. So 38 plus 50 plus 37 plus 44 plus 46 plus 48 plus 38 plus 46. Why are the numbers so many? How many? So we add all of these values up together, and then we divide it by the number of values we have. So 1, 2, 3, 5, 6, 7, 8, 9, 10, 11. And so we end up with the mean is 44. Okay, now conveniently, this is the correct answer. And because I'm kind of tired, I'm not going to go through the others, but to explain how to do it, for the median, what you want to do is you want to line them up in order from smallest to largest. So in this case, you'd start with 38, 38. And then what you do is you start crossing out from the edges. So you remove the largest number, remove the smallest number, until you end up with one number, which is the number that's in the exact middle, and that's your median. Okay? For the range, that's fairly straightforward. You just take the biggest value, and then you subtract from it the smallest value. And so 53 minus 38, that's 15, not 16, and so this answer is wrong. And then the variance, which, no thank you, no thank you. I mean, we already found the mean to be correct. Honestly, it's probably easier in the exam if you figure out whether or not the variance is the correct answer by exclusion. because it takes a long time to find in like the actual exam time. Okay, can mutually exclusive events be independent? No. The reason for that is that if you have two events that are mutually exclusive, the moment one happens, the other one can't happen, right? And so they are affecting each other, whereas independent events don't affect each other. Okay? And so this we went over the previous lecture, so I'm not really going to repeat unless someone asks, which means you guys would be very sadistic. Okay, so the probability of the Al Faisal campus computer working when you want to do homework is 95%, and the probability of all computers being busy when you need a computer is 85%. So what's the probability of being able to do your homework when you are basically ready? All right. And so these are effectively two independent events. And so what we want to do is what's the probability that your computer works, okay, and not all of the computers being busy. And so step one here, okay, is 1 minus 0.85. So that's going to be 0.15. Step two is multiply 0.15 by 0.95. And so that's going to be 0.1425. Okay? Intro to epidemiology. An epidemiologist is doing a study on the sleep pattern of students, but does not provide any intervention. What type of study is this? Because they're not providing any intervention, then it's an experimental study. Qualitative, we don't really have any information on whether it's qualitative or quantitative. And so the answer is observational, and it's observational because they're just looking at the sleep patterns of students without providing any intervention. And finally, epidemiologists use a model for studying infectious disease and its spread that involves the microbe that causes the disease. Epidemiologists use a model for studying infectious disease and its spread. The model involves a microbe that causes the disease, an organism that harbors the disease, and the external factors. This is also known as, so we have the organism that involves the disease, which is the agent, the organism that harbors the disease, so that's the host, and the external factors, which is the environment. And so what has the agent, host, and environment? Well, of these options, that's option A. The vector is the specific animal that will spread the microbe, and then transmission is how the microbe spreads. So it could be through a vector, or it could be through the air, and so on. Okay, and I think that's it for the questions. If anyone has any questions, I'd appreciate it if you ask now. If nobody has any questions, I think I'm going to wrap up. Thank you so much, everyone, for attending, and I hope I was able to answer you guys' questions.